So today we're going to carry on with differentiation. However, I got asked a couple of questions based on Monday's lesson, okay? Based on this idea of an exponential, okay? So you remember, if I give you something like y equals 2 to the power of x, yeah? This is called an exponential, right? Why is it an exponential? What makes it an exponential?
The graph rise up, the values rise up exponentially. So
What does exponential mean though? What type of growth is it? What's happening?
it's like
Increasing really fast.
It's increasing really fast. In other words, if this was time and this was like amount of money in my bank account, what would my money be doing with every time period? It'd be multiplying by 2. This is what it tells you it grows by. There's a growth factor. Yeah? So this is an exponential function. It's basically where it multiplies by the same amount every single time. Now, I said to you that the rate of change, in other words, when I differentiate this thing, of my function is proportional to its size. Is proportional to its size, okay? In other words, the amount of, so how quickly my money is growing is proportional to how much money I have. And that kind of makes sense intuitively, okay? All this means is that the more money I have, the faster it can grow. That makes sense? Think about interest rates. If I put £1 into my bank account, it's not going to grow very, very quickly. Whereas if I put £1 million in my bank account, well, that's going to grow much, much faster. Yeah? So it's going to go, instead of going, say, for example, it's 2, right? The growth factor is 2. If I put £1 into my bank account, after 1 year, I'll have £2. Then after another year, I'll have £4. Whereas if I put £1 million in my bank account, after 1 year I'm going to have £2 million, right? That's even bigger than £2, right? And then I'll have £4 million and £8 million, etc., etc., etc. Yes.
Alex, in last lesson you said if we multiply 2 over x with some value,
Yeah.
You said it was our starting value.
Exactly. So in this case, because there's just a 1 written there, that is my starting value. It's £1.
So we have £1 in our bank account.
Yes.
Okay.
Okay. But the point is, I just wanted to get the idea of exponential growth across. It's multiplying by the same amount each time. This value in front of it tells you what you start with. Okay? Right. So this is the fundamental relationship which I wanted to get across. That how quickly something can grow by is proportional to its size. Okay? If it helps, visualize this. So let's imagine this is a hill, okay? So let's imagine a cross-section of a hill, and it's a snowy hill, so there's snow on it. And I start off with a snowball at the top, okay? So a little tiny snowball in my hand. Now, as I roll the snowball down the hill, are you happy that it will start to pick up more and more snow? Yeah? Because it means its surface area will increase, yeah? So in other words, as it rolls down the hill, its surface area increases. In other words, its rate of change increases. And the more it rolls down the hill, the more the surface area there is, the more snow that can stink to it. In other words, the bigger my snowball is, the faster it can grow because there's going to be more surface area. Okay? So this would be an example of exponential growth. Okay? The bigger something is, the faster it can grow. The bigger something is, the faster it can grow. That's all I wanted to get across by this idea of proportionality. But what it means with proportionality, if I wanted to convert this into an equation rather than just a relationship, is that dy by dx, the rate of change, would be equal to some multiple of its size. Does that make sense? Yeah? So it's some multiple of its size. That's what proportional means. Okay? And I said, well, okay, this would be true for, like, for example, y equals 2 to the power of x, or y equals 3 to the power of x, or y equals 5 to the power of x. But if I started off with a very special base, which is y equals, can anybody remember?
E over
e to the power of x, okay, where e is like 2.718, etc., etc., etc. Okay, it's an irrational number, it's like pi, okay. Then in that case, the rate of change would not just be proportional, be extra, it would be exactly equal to it. Okay, it would be equal to it. Okay, so in other words, the rate of change when you've got e as your base would be exactly equal to its size. Does that make sense to everyone?
because yeah, true.
Yeah, does that make sense? So in general, with the exponential functions, rate of change is proportional to its size. It means it's always going to be off by some factor. But with a base of e, it's not just proportional, it's equal to. It's exactly the same as its size. Okay? Is that clear to everyone? Yep. Did we read in the notes where e came from as well? Did we read in the notes, which I asked you to read,
Oh,
where
yeah,
E
I
came
mean,
from?
in the notes it says something about being nature, because in nature there's an exponential thing going
Yep.
on, and it goes with, you know,
Oh, yeah.
with factor of E.
Yeah.
Is everything all right?
Yes, exactly. So in general, if you have, in nature, if you have this idea of continuous growth. So this was, the example which I gave up here, was considering what would happen like every minute. So you basically look at a minute, you then look away, wait for it to grow, then look back a minute later, and then look away and then wait for it to grow and then look back a minute later. But if you look at it over continuous time periods, in other words, you keep looking at it, you keep looking at your money, then in general it will always grow according to E. Okay, so that if you like, this would be discrete growth. In other words, you're considering what happens at minute intervals, whereas this would be continuous growth. In other words, you never stop looking at it. You're constantly looking at the growth. Okay, so that's another difference between them. But I really just wanted to emphasize the fact of why this makes sense. Why this makes sense. If there's time at the end, I can talk you through the notes if you want to understand where E comes from. But for the time being, this is enough, I think. This is enough.
So E continuous, I missed the part continuous thing.
Okay, so effectively, let's suppose that this is money. So let's suppose Y is money, the amount of money that I have in my bank account,
Yeah.
and X is time. Okay, X represents time. So for this situation, what I'm saying, if I draw this as a timeline, let's suppose my time interval is given in minutes, okay? At the start, at the 0th minute, how much money will I have?
1.
Yeah, £1. And then I look away, I wait for the money to grow, and then I come back to it, and I look a minute later, okay? How much money will I have a minute later?
2.
Yeah, and then I look away, wait for it to grow, go off to do something else, wait for it to grow, come back a minute later, how much money will I have? 4, and so on. So at 3 I'll have £8. But my point is, because I'm where I'm looking at my money, I'm looking at it on the minute, if you like. Or if this was years, I'd look at it at the end of every single year. With continuous growth, what I mean by continuous growth is I never stop looking at it. Okay? In other words, instead of waiting for it to get between 0 and 1, I look at it, for example, at really, really close, so I never stop looking at it. Okay? So I'm literally measuring it all the time. This will become clear. I would like to go through that, but I need to get through other stuff first. So I'll come back to this if there's time.
Okay.
Okay? Anyway, at the end of last lesson, we came up, or we looked at how we could differentiate trigonometric functions, so sine and cos, and also exponential functions, sort of. Okay? So can anybody remember, if I differentiate sine, differentiates to cosine. Yoji, if you differentiate cosine, what do you get? Differentiate this. Good, well done. Yeah, you in. If you differentiate negative sine, what do you get? Perfect. And somebody else, if you differentiate negative cos, what do I get? Back to sine again, okay? So this is a table, if you like, of derivatives. Okay, so if I differentiate, it goes like this. And I said it was cyclic differentiable.
Sorry, my phone.
Okay, you happy with this? We looked at this? Yeah, we looked at why it's true. Okay, also, I came up with this relationship. I said if I have y equals e to the x, if that's my function, what do I get if I differentiate this? E to the power of x. Perfect. And also, if I take the natural logarithm of x, which remember is basically the same thing, but looked at, instead of saying you give me time and I tell you the amount of money, it literally says you tell me the amount of money and I give you time. If I differentiate this, what do I get? Absolutely, and I proved that to you. So I came up with these sort of 3 fundamental relationships at the end of last lesson. Okay,